Scientists pointed their most powerful telescopes at black holes. What they found broke every expectation. Matter spirals inward toward certain doom. At the exact same time, blazing jets of material rocket outward at incredible speeds. This seems like a cosmic contradiction. How can something that swallows everything also be spitting matter back out? The answer lies right at the edge of the black hole. There's a boundary in space where the pull becomes so strong that nothing can escape. Scientists call this the event horizon. Just outside this boundary, something extraordinary happens. In falling, matter doesn't fall straight down. It forms a spinning disk of superheated material. This disk becomes one of the brightest objects in the universe. The same process that creates the disk also launches powerful jets of material into space. Black holes aren't just cosmic vacuum cleaners. They're the universe's most efficient engines for both destruction and creation. Black holes don't hunt for their food. They wait for it to come to them. When a star wanders too close, gravity takes over. The black hole's pull becomes irresistible. But matter doesn't simply fall straight into a black hole. It has what scientists call angular momentum. Think of it like cosmic spinning motion that can't be destroyed. This spinning forces the captured material to spiral inward gradually. Layer by layer, it forms a flat, rotating structure around the black hole. Astronomers call this an accretion disk. It's essentially a cosmic feeding tray. The disk glows white-hot from friction between its layers. Material in the inner regions moves faster than outer regions. This creates intense heat and brilliant light. Some accretion disks shine brighter than entire galaxies. The feeding process can continue for millions of years. As long as material keeps falling toward the black hole, the disk keeps glowing. This transforms invisible monsters into some of the most luminous beacons in the cosmos. Here's the universe's strangest paradox. The black holes that eat the most also shine the most. The more material they devour, the more brilliantly they beacon across cosmic distances. When matter crashes into the accretion disk, it releases tremendous energy. The collisions heat the material to temperatures of millions of degrees. At these extreme temperatures, the disk radiates intense light across the entire electromagnetic spectrum. Active feeding creates what astronomers call an active galactic nucleus. These become so bright they can outshine the combined light of hundreds of billions of stars. Some can be seen from billions of light years away. The brightness directly relates to the feeding rate. Black holes consuming large amounts of material per year create the most spectacular light shows. Those on starvation diets remain nearly invisible. This relationship revealed how black holes grow over cosmic time. The brightest episodes mark periods of rapid growth when black holes gained most of their mass. Today's quiet giants were yesterday's blazing beacons. Material falling into a black hole doesn't remain cold and dark. Gravity transforms it into one of the hottest environments in the universe. The process begins as soon as matter starts its final journey inward. Friction between spinning layers heats the accretion disk to incredible temperatures. Inner regions, moving fastest, reach temperatures exceeding those found in stellar cores. The material becomes so hot it radiates across all wavelengths of light. Different parts of the disk glow different colors based on their temperature. Outer regions appear red and relatively cool. Middle sections burn white-hot. The innermost areas blaze with blue and ultraviolet light. This heating process converts gravitational energy into thermal energy with remarkable efficiency. Matter falling into a black hole releases more energy per unit mass than nuclear fusion reactions powering stars. The temperature gradient creates a natural cosmic thermometer. By measuring the colors and brightness of the accretion disk, astronomers can map the temperature structure and determine how rapidly material approaches the event horizon. Not all material falling toward a black hole crosses the event horizon. Some gets redirected into narrow beams that shoot away from the black hole at incredible speeds. These relativistic jets represent one of nature's most powerful acceleration mechanisms. The jets form along the black hole's rotation axis. Magnetic fields threading through the accretion disk become twisted by the black hole's spin. This twisting creates a cosmic launcher that hurls charged particles outward. Jet speeds approach the speed of light itself. Material that seemed destined to disappear forever instead rockets across intergalactic distances. Some jets extend for millions of light years, far beyond their host galaxies. The jet formation requires specific conditions. The black hole must be spinning rapidly and surrounded by a magnetized accretion disk. Without both ingredients, no jets form and all material simply falls inward. These cosmic fire hoses can affect entire galaxy clusters. They heat surrounding gas, trigger star formation in some regions, and suppress it in others. Black hole feeding thus influences cosmic evolution on the largest scales. Black hole accretion represents the most efficient energy conversion process known in the universe. It converts matter to energy more effectively than any other natural phenomenon, including the nuclear fusion powering stars. Einstein's famous equation, E=mc², shows that mass contains tremendous stored energy. Nuclear fusion in stars converts about 1% of mass into energy. Black hole accretion can convert up to 40% of infalling mass into radiated energy. This incredible efficiency comes from gravity's strength near black holes. The gravitational field becomes so intense that even small amounts of infalling matter release enormous energy when heated by friction and compression. A black hole consuming just one Earth mass of material per year would outshine our entire sun. This explains how relatively small black holes can power phenomena visible across billions of light years. The energy conversion occurs in the accretion disk, not inside the black hole itself. Once matter crosses the event horizon, its energy becomes permanently trapped. The observable fireworks happen just outside the point of no return. Magnetic fields threading through accretion disks don't just passively follow the matter. They actively control how material spirals inward and determine whether jets form. These invisible force fields act like cosmic traffic controllers. The magnetic field lines get twisted and amplified by the disk's differential rotation. Inner regions spin faster than outer regions, wrapping field lines into increasingly tight spirals. This creates magnetic pressure that can overpower gravity. When magnetic forces become strong enough, they redirect infalling matter. Instead of continuing inward, charged particles follow magnetic field lines outward along the rotation axis. This magnetic launching mechanism creates the observed jets. The same magnetic fields that create jets also transport angular momentum outward through the disk. This allows material to lose its spinning motion and fall closer to the black hole. Without this magnetic brake, most matter would remain in stable orbits. Magnetic field strength varies dramatically between different black hole systems. Strong fields create powerful jets and efficient accretion. Weak fields allow matter to spiral inward without producing significant jets or heating. Spinning black holes possess enormous rotational energy stored in their angular momentum. This energy can be extracted through a remarkable process that essentially allows the black hole's spin to power the surrounding accretion flow in jets. The extraction mechanism requires magnetic field lines that thread from the accretion disk into the black hole's ergosphere. This is a region outside the event horizon where space-time itself rotates with the black hole. Field lines in this region get dragged along by the spinning space-time. As the magnetic fields rotate, they act like cosmic generators. The spinning field lines accelerate charged particles and transfer energy from the black hole's rotation to the surrounding material. This process can power jets for millions of years. The energy extraction rate depends on how fast the black hole spins. Rapidly rotating black holes can power more luminous jets and accretion disks than slowly spinning ones. The fastest spinners convert rotational energy most efficiently. Over cosmic time, this process gradually slows down the black hole's rotation. The rotational energy gets transferred to jets and radiation. Eventually, the spinning giant becomes a slowly rotating energy source that has powered cosmic fireworks for eons. When a star wanders too close to a massive black hole, tidal forces tear it apart before it can cross the event horizon. The black hole's gravity becomes stronger on the star's near side than its far side, creating a differential pull that overcomes the star's own gravity. The tidal force stretches the star into a long, thin stream of gas. Astronomers call this process tidal disruption. Half the stellar debris gets flung away into space, while the other half falls back toward the black hole. The returning material doesn't fall straight down. It maintains some orbital motion and forms a temporary accretion disk around the black hole. This disk becomes extremely hot and bright as the stellar debris crashes together. Tidal disruption events create spectacular cosmic flares that can briefly outshine entire galaxies. These flares allow astronomers to discover black holes that were previously invisible because they weren't actively feeding. The flare brightness depends on the star's mass and how close it approached before disruption. Larger stars create brighter flares, while smaller stars might be completely consumed without creating visible fireworks. The timing reveals details about both the star and the black hole. Black hole feeding doesn't just affect the immediate vicinity around the black hole. The energy and jets produced during active feeding can influence star formation and gas heating across entire galaxies and beyond. When jets plow through surrounding gas, they create shock waves that heat the material to millions of degrees. This heated gas becomes too hot to collapse and form new stars. Active black holes can thus regulate star formation across their host galaxies. The feedback process helps explain why the most massive galaxies contain the largest black holes. As black holes grow through feeding, their increased activity suppresses further star formation. This limits how large galaxies can become. In galaxy clusters, black hole jets can heat gas across millions of light years. This prevents the gas from cooling and falling into the central galaxy. Without this heating, central galaxies would grow much larger than observed. The feedback effects create a cosmic balance between black hole growth and galaxy evolution. Black holes regulate their own food supply by heating surrounding gas and suppressing the formation of new stars that could eventually feed them. Modern telescopes have captured the black hole feeding process in remarkable detail. X-ray observations reveal the hot accretion disk glowing around black holes, while radio telescopes trace the jets extending far beyond the host galaxy. X-ray telescopes detect characteristic spectral lines from iron atoms in the accretion disk. These lines are stretched and shifted by the black hole's intense gravity and the rapid orbital motion of the hot gas. The line shapes reveal the black hole's mass and spin rate. Radio telescopes map jet structures across multiple scales. Very long baseline interferometry can resolve details smaller than our solar system in jets located billions of light years away. These observations show material accelerating from nearly stationary to near light speeds. Time variability studies reveal how quickly the accretion process changes. Some black holes brighten or dim on timescales of hours to days. These rapid changes confirm that the emission comes from regions very close to the black hole where orbital periods are short. Multi-wavelength observations combining X-ray radio, optical, and gamma-ray data provide comprehensive views of the feeding process. Coordinated monitoring campaigns track how changes in the accretion disk affect jet production and vice versa, confirming theoretical models of black hole feeding. Why doesn't matter fall straight into a black hole like a rock dropping into a well? The answer lies in a fundamental rule of physics that governs all spinning motion in the universe. Every piece of matter falling toward a black hole carries something called angular momentum. Think of it as the tendency to keep spinning or orbiting. This spinning motion cannot simply disappear. When gas or debris approaches a black hole, it's usually moving sideways as well as inward. The black hole's gravity pulls the material toward the center, but the sideways motion forces it to curve into an orbit instead of falling directly down. As the material spirals inward, it naturally flattens into a disk shape. Inner regions move faster than outer regions, just like planets closer to the Sun orbit faster than distant ones. This creates the characteristic accretion disk structure. The conservation of angular momentum explains why black holes develop these spinning feeding disks rather than simply swallowing matter directly from all directions. Different parts of the accretion disk don't rotate as one solid unit. Instead, material closer to the black hole orbits much faster than material farther out. This creates friction between the layers. When neighboring regions of gas move at different speeds, they rub against each other. This rubbing generates heat through a process astronomers call viscous heating. It's similar to how rubbing your hands together warms them up. The friction gradually removes energy from the orbiting material. As the gas loses energy, it spirals closer to the black hole. The lost orbital energy gets converted directly into heat that makes the disk glow. This heating process occurs throughout the entire disk structure. The faster the speed difference between adjacent layers, the more friction and heat gets generated. Most of the disk's incredible brightness comes from this friction rather than the black hole itself. Viscous heating transforms the gravitational energy of infalling matter into thermal energy that creates one of the brightest phenomena in the universe. The temperature across an accretion disk varies dramatically with distance from the black hole. Material near the center reaches temperatures that dwarf even the hottest stellar cores. Regions closest to the black hole move at the highest orbital speeds. This creates the most intense friction and heating. Inner disk temperatures can exceed 10 million degrees Celsius. That's nearly 1,000 times hotter than the Sun's surface. As you move outward through the disk, temperatures drop steadily. Middle regions might reach only a few million degrees, while outer edges remain relatively cool at thousands of degrees. The entire disk glows like a cosmic rainbow of temperatures. This temperature gradient creates the disk's characteristic appearance. Inner regions blaze with blue and ultraviolet light. Middle sections shine white hot. Outer areas glow red like a cooling ember. The temperature distribution directly maps the energy release from gravitational heating, with the most intense heating occurring where orbital speeds are fastest. There's a critical distance around every black hole where the rules of orbital motion break down completely. Inside this boundary, matter cannot maintain a stable orbit no matter how fast it moves. Astronomers call this the innermost stable circular orbit. It represents the final traffic circle before the event horizon. Material can orbit at this distance, but any closer approach leads to inevitable capture. The location of this boundary depends on how fast the black hole spins. For non-rotating black holes, stable orbits end at about 3 times the event horizon radius. Rapidly spinning black holes allow material to orbit much closer before losing stability. Once matter crosses this boundary, it falls rapidly inward with no possibility of escape. The orbital velocity required for stability would exceed the speed of light, which physics forbids. This represents the final checkpoint wherein falling material transitions from controlled orbital decay to free fall toward the event horizon. Accretion disks appear massive and substantial, but they're actually remarkably thin compared to their enormous diameter. The disk's thickness results from a delicate balance between competing forces. Gravity tries to pull all the hot gas downward toward the black hole, but the gas pressure from the heated material pushes outward and upward, trying to expand the disk. These forces reach an equilibrium that determines the disk's height. A typical accretion disk spans millions of kilometers in diameter, but measures only thousands of kilometers thick. That's like a dinner plate with the thickness of a sheet of paper. The proportions are incredibly flat. The disk maintains this flatness because any gas that rises too far above the midplane gets pulled back down by gravity. Material that tries to compress too much gets pushed out by pressure. The balance creates a stable, thin structure. This extreme flatness concentrates the disk's mass and energy into a narrow plane, making the heating and radiation processes far more efficient than if the material were spread throughout a thick, spherical cloud. At the most extreme temperatures, something remarkable happens in accretion disks. The hot gas produces so much light that the light itself begins to push outward with tremendous force. When matter reaches temperatures of millions of degrees, it radiates intense electromagnetic energy across all wavelengths. This radiation carries momentum and exerts pressure on the surrounding gas, just like wind pushing against a sail. In the hottest regions of the disk, radiation pressure can become stronger than gas pressure. The photons produced by the heated material push outward against the black hole's gravitational pull. This creates a cosmic tug-of-war between light and gravity. Radiation pressure helps support the disk's structure and can even drive material away from the black hole. In extreme cases, the radiation becomes so intense it overpowers gravity and blows matter outward in powerful winds. This process limits how rapidly black holes can grow by creating natural feedback that reduces the rate at which matter can fall inward. Accretion disks don't rotate smoothly like solid wheels. Instead, they become violently turbulent due to magnetic forces threading through the conducting gas. This turbulence plays a crucial role in the disk's evolution. The turbulence arises from something called magnetorotational instability. Magnetic field lines connecting different parts of the disk get stretched and twisted by the differential rotation. When the stretching becomes too extreme, the field lines snap and reconnect violently. These magnetic disruptions create swirling motions that transport angular momentum outward through the disk. This allows material to lose its spinning motion and spiral closer to the black hole. Without this process, matter would remain trapped in stable orbits. The turbulent motions also generate additional heating beyond simple viscous friction. The chaotic magnetic activity converts orbital energy into thermal energy, contributing to the disk's brightness and temperature. Magnetic turbulence essentially acts as the disk's engine for both angular momentum transport and energy dissipation. Different temperatures produce different colors of light. This fundamental relationship allows astronomers to map accretion disk structure just by analyzing the light that reaches Earth. Hot objects emit light across a broad spectrum, but the peak wavelength depends on temperature. Blue and ultraviolet light comes from the hottest regions. Visible white light originates in moderately hot areas. Infrared radiation emerges from the coolest outer zones. By measuring the intensity at different wavelengths, astronomers can determine the temperature distribution across the entire disk. This technique reveals not only the disk's structure, but also the black hole's mass and spin rate. The total brightness across all wavelengths indicates how rapidly matter falls into the black hole. Brighter disks mean higher accretion rates and more violent feeding. Dimmer disks suggest the black hole is on a starvation diet. Spectral analysis transforms the colors of distant light into detailed maps of these cosmic feeding processes. The rate at which matter falls into a black hole directly controls how brightly the accretion disk shines. This relationship allows astronomers to measure cosmic appetite from across the universe. When a black hole feeds rapidly, consuming multiple Earth masses of material per year, the accretion disk becomes extraordinarily bright. Fast feeding creates more friction, higher temperatures, and more intense radiation across all wavelengths. During periods of slow feeding, the same black hole might consume less material than a small asteroid contains. The reduced friction creates lower temperatures and dimmer emission. The disk might barely be detectable even with powerful telescopes. Some black holes experience dramatic changes in their feeding rate over human timescales. They can brighten or dim by factors of hundreds or thousands as their food supply varies. These changes reveal the chaotic nature of matter delivery to black holes. The accretion rate acts like a cosmic dimmer switch that controls the brightness of some of the most luminous objects in the universe. Accretion disks cannot maintain perfectly steady feeding rates. Instead, they experience cycles of buildup and release that create spectacular periodic outbursts visible across cosmic distances. The instability arises when matter accumulates in the outer disk faster than it can spiral inward. This creates a traffic jam of material that gradually builds up mass and density in the outer regions. Eventually, the accumulated material becomes unstable and cascades rapidly inward toward the black hole. This sudden feeding episode creates a dramatic brightening as the increased accretion rate generates intense heating and radiation. After the outburst, the disk returns to a quieter state until enough material accumulates again to trigger the next cycle. Some black holes repeat this pattern with remarkable regularity over periods ranging from months to decades. These instability cycles reveal that black hole feeding operates more like a series of cosmic meals than a steady diet. Imagine a cosmic dynamo that gets stronger the more it spins. That's exactly what happens inside accretion disks when magnetic fields interact with rotating gas. The disk doesn't rotate like a solid wheel. Inner regions spin much faster than outer regions. This difference in rotation speed stretches and twists magnetic field lines that thread through the gas. As the field lines get stretched, they become stronger and more unstable. Eventually, they snap back like rubber bands, creating violent magnetic reconnection events. These magnetic explosions generate turbulence throughout the disk. The turbulent motions transport angular momentum from inner regions to outer regions. This magnetic shuffling allows material to lose its spinning motion and fall closer to the black hole. Without this magnetorotational instability, material would remain trapped in stable orbits forever. The magnetic turbulence acts as the disk's essential transport system for both matter and energy. Deep in the hottest parts of accretion disks, light itself becomes a major player in the physics. The radiation produced by the heated gas creates pressure that can overpower the gas particles themselves. When temperatures reach millions of degrees, the hot gas produces intense electromagnetic radiation. This radiation carries energy and momentum, pushing outward against surrounding material, just like wind pressure. In normal circumstances, gas pressure dominates the disk's structure, but in the innermost regions, radiation pressure can become 10 times stronger than gas pressure. The photons push harder than the gas particles. This radiation dominance changes how the disk behaves. Material can be blown outward by light pressure rather than falling inward due to gravity. The disk becomes unstable and prone to violent eruptions. Radiation pressure creates a natural limit on how much matter can fall into a black hole by generating powerful outflows that carry material away from the feeding zone. Hot material rises while cool material sinks. This simple principle creates complex circulation patterns inside accretion disks when temperature differences become extreme. Convection occurs when the temperature drops too rapidly with height above the disk midplane. Hot gas at the bottom becomes buoyant and rises upward, while cooler gas descends to replace it. These motions create rolling circulation cells. The convective motions transport heat more efficiently than simple radiation or conduction. Instead of energy slowly diffusing outward, hot gas physically carries thermal energy to cooler regions through bulk motion. Convection also helps mix material throughout the disk structure. Elements and isotopes get stirred together, creating more uniform chemical composition than would occur through diffusion alone. The circulation patterns add another layer of complexity to disk dynamics, creating three-dimensional flows that interact with magnetic fields and turbulence to shape the disk's evolution. Most accretion disks hide their deepest secrets behind an impenetrable fog of their own making. The dense, hot material blocks light from escaping until it reaches the disk's surface layers. Optical thickness measures how far light can travel through material before being absorbed or scattered. In the dense inner regions of accretion disks, this distance becomes extremely small. Light photons produced in the disk's interior collide repeatedly with electrons and ions. Each collision changes the photon's direction and can absorb its energy entirely. Most photons never escape from where they were created. Only photons produced near the disk surface can travel freely into space. This means we can only observe the outermost skin of the accretion disk, not its interior structure directly. The opacity creates a natural photosphere, similar to the sun's visible surface, where the disk transitions from opaque interior to transparent exterior. Above many accretion disks floats a cloud of extremely hot plasma that creates some of the most energetic radiation in the universe. Astronomers call this region the corona. The corona contains gas heated to temperatures exceeding 100 million degrees. At these extreme temperatures, the plasma emits high-energy X-rays that can penetrate through almost any material. How the corona forms remains partially mysterious. Magnetic field lines rising from the disk may heat the plasma through violent reconnection events. Alternatively, shock waves from the disk surface might compress and heat the overlying gas. The hot corona illuminates the accretion disk below like a cosmic searchlight. Hard X-rays from the corona strike the disk surface and get reflected back toward Earth with characteristic spectral signatures. Corona emission provides crucial information about the extreme physics occurring near black holes, revealing processes that cannot be studied anywhere else in the universe. Perfect black bodies exist only in physics textbooks. Real accretion disks produce radiation that deviates significantly from ideal blackbody curves due to complex interactions between photons and charged particles. Compton scattering occurs when high-energy photons collide with free electrons in the hot plasma. These collisions change the photon's energy and direction, creating spectral features that reveal the plasma's temperature and density. Free radiation happens when electrons accelerate in the electric fields of ions. This process, also called bremsstrahlung, adds extra emission across a broad range of wavelengths. The combination of scattering and free emission modifies the disk spectrum in characteristic ways. Astronomers use these deviations from blackbody radiation to diagnose physical conditions throughout the disk structure. Spectroscopic analysis of these modified spectra reveals details about electron temperatures, densities, and velocities that would be impossible to determine from simple thermal emission alone. Magnetic fields don't just thread passively through accretion disks. They actively rise toward the surface through a buoyancy mechanism discovered in studies of stellar atmospheres. The Parker instability occurs when magnetic pressure becomes locally stronger than gas pressure. Magnetic field lines act like bubbles of low-density material that want to rise upward through denser surrounding gas. As field lines rise, they drag ionized gas along with them. This creates magnetic loops and structures that emerge from the disk's interior and break through the surface layers. The emerging magnetic fields can reconnect violently when opposite polarities meet above the disk surface. These reconnection events release stored magnetic energy and heat the surrounding plasma to extreme temperatures. Parker instability provides a mechanism for transporting magnetic flux from the disk interior to the corona and jets, playing a crucial role in launching material away from the black hole. In the most extreme temperature regions, Einstein's famous equation E=mc² operates in reverse. Pure energy transforms back into matter through pair production of electrons and their antimatter twins. When photon energies exceed twice the electron rest mass energy, the photons can spontaneously convert into electron-positron pairs. This threshold corresponds to temperatures of about 6 billion degrees. The newly created particle pairs add to the plasma density and pressure. More particles mean more scattering events and more complex radiation processes. The disk becomes even more opaque to its own radiation. Pair production creates a feedback loop that regulates the disk temperature. As temperatures rise, more pairs form, increasing the opacity and trapping more radiation. This limits how hot the disk can become. The process represents one of the most direct conversions between energy and matter occurring naturally in the universe, demonstrating fundamental physics under extreme conditions. Close to black holes, Newton's laws of gravity break down completely. Einstein's general relativity takes over, creating effects that dramatically alter how matter moves and light propagates. Space-time itself becomes curved by the black hole's enormous mass. This curvature acts like a cosmic funhouse mirror that distorts distances, time, and angles for everything moving through the region. particles orbiting near the black hole experience time dilation. Their clocks run slower compared to distant observers. Light gets redshifted and blue-shifted depending on the motion of its source relative to the black hole. The curved spacetime creates additional forces on orbiting material beyond simple Newtonian gravity. These relativistic corrections affect orbital stability and the location of the innermost stable orbit. Frame dragging occurs around spinning black holes, where the rotation literally drags spacetime around with it. This affects the direction of particle orbits and magnetic field orientations near the event horizon. At the most extreme temperatures, accretion disks develop an invisible cooling system that operates through some of the most elusive particles in the universe. When plasma temperatures exceed billions of degrees, nuclear reactions can produce neutrinos. These nearly massless particles interact so weakly with matter that they escape directly from the disk's interior without obstruction. Unlike photons, which get trapped and scattered repeatedly, neutrinos stream freely out of even the densest regions. They carry thermal energy away from the disk's core, providing an efficient cooling mechanism. Neutrino cooling becomes dominant at the highest temperatures, preventing runaway heating that might otherwise make the disk unstable. The cooling effect helps regulate the disk's thermal structure. The process represents one of the few direct connections between nuclear physics and black hole astrophysics, as neutrino production rates depend on fundamental particle interactions occurring in the extreme environment. Iron atoms in accretion disks serve as cosmic fingerprints that reveal the disk structure and the black hole's properties. When X-rays strike iron nuclei, they create distinctive spectral lines that astronomers can detect across billions of light years. The K-alpha line forms when high-energy X-rays knock electrons out of iron atoms' inner shells. Electrons from outer shells fall down to fill the gaps, emitting characteristic X-ray photons with a specific energy signature. Near black holes, these iron lines get distorted by relativistic effects. The rapid orbital motion of the iron-rich gas creates Doppler shifts that broaden the spectral lines into distinctive asymmetric profiles. Gravitational redshift also affects the iron line emission. Photons climbing out of the black hole's gravitational well lose energy, shifting the line to lower frequencies in a way that depends on the emission radius. The detailed shape of the iron K-alpha line profile allows astronomers to map the inner structure of accretion disks and measure black hole spin rates with remarkable precision. Light struggles to escape from the intense gravitational fields near black holes. As photons climb outward, they lose energy in a process that fundamentally alters the disk's observable properties. Gravitational redshift occurs because photons must do work against gravity to escape from deep in the gravitational well. This work comes from the photon's own energy, reducing its frequency and shifting it toward redder wavelengths. The effect becomes stronger closer to the black hole. Light from the innermost disk regions suffers the most severe redshift, while emission from outer regions experiences less gravitational influence. Observers far from the black hole see a disk spectrum that's systematically redshifted compared to what local observers near the disk would measure. This gravitational signature provides another tool for probing strong field gravity. The redshift effect combines with Doppler shifts and relativistic beaming to create complex spectral patterns that encode information about both the disk structure and the spacetime geometry around the black hole. What happens when you twist a rubber band until it's ready to snap back? Something similar occurs with magnetic fields around spinning black holes, but with far more explosive results. Magnetic field lines thread through the accretion disk like invisible wires. The disk rotates at one speed, while the black hole spins at a different rate. This differential rotation gradually winds up the magnetic field lines into tight spirals. As the field lines get twisted more and more, they store enormous amounts of magnetic energy. Think of it like winding up a cosmic spring. The more twisting that occurs, the more energy gets stored in the magnetic configuration. Eventually, the twisted field lines become unstable and release their stored energy violently. This sudden energy release can accelerate nearby charged particles to incredible speeds. The twisting process transforms the rotational energy of the disk and black hole into magnetic energy that powers some of the most powerful jets in the universe. Charged particles near black holes experience forces that don't exist in everyday life. When magnetic fields rotate, they create a centrifugal effect that can fling particles outward at tremendous speeds. The rotating magnetic field acts like an invisible carousel. Charged particles get caught up in this rotation and feel a force pushing them away from the rotation axis. The faster the magnetic field spins, the stronger this outward force becomes. Unlike a mechanical carousel, there's no physical structure limiting how fast particles can be thrown outward. The magnetic centrifugal force can accelerate particles to significant fractions of light speed. This process preferentially affects particles moving along the black hole's rotation axis. Material in other directions experiences weaker magnetic forces and remains bound to the accretion disk. The magnetic centrifugal mechanism provides the initial acceleration that launches material away from the black hole's gravitational grip and into the relativistic jets. Energy and angular momentum don't just disappear when material falls toward a black hole. Instead, they get transported outward through the magnetic field in a process discovered by physicist John Poynting. Electromagnetic fields can carry both energy and angular momentum, just like moving matter does. When magnetic field lines connect the spinning black hole to the surrounding plasma, they create pathways for energy transport. The Poynting flux represents the flow of electromagnetic energy along magnetic field lines. This energy stream carries angular momentum from the black hole and disk outward to distant regions. As electromagnetic energy flows outward, it can transfer momentum to charged particles along the way. This momentum transfer provides additional acceleration to material being launched in jets. The Poynting vector transport allows black holes to power jets using their own rotational energy, creating a cosmic energy transmission system that operates across vast distances. Magnetic fields can squeeze and shape plasma just like a garden hose nozzle concentrates water flow. This magnetic focusing plays a crucial role in creating the narrow, high-speed jets observed from black holes. Magnetic pressure acts on charged particles similar to how gas pressure affects neutral matter. Strong magnetic fields can compress plasma into increasingly narrow channels. As the plasma gets squeezed into a smaller cross-sectional area, it must speed up to conserve mass flow. This is similar to how water accelerates when flowing through the narrow opening of a nozzle. The magnetic nozzle effect becomes stronger closer to the black hole where magnetic field strengths reach their maximum values. The most dramatic acceleration occurs in the innermost regions. This focusing mechanism explains why black hole jets remain collimated into narrow beams across enormous distances, rather than spreading out like a diffuse wind. Can you steal energy from a black hole? The answer is yes, if you know how to tap into its rotation through one of the most elegant processes in theoretical physics. The Blandford-Znajek mechanism operates in the ergosphere, a region outside the event horizon where space-time itself gets dragged around by the spinning black hole. In this zone, magnetic field lines can extract rotational energy. Magnetic field lines threading from the disk into the ergosphere get twisted by the rotating spacetime. This twisting creates electromagnetic fields that propagate outward, carrying energy away from the black hole. The energy extraction rate depends on the black hole's spin speed and the strength of magnetic fields threading through the ergosphere. Rapidly spinning black holes with strong magnetic fields can power the most luminous jets. Over cosmic time, this process gradually slows down the black hole's rotation as its spin energy gets converted into jet power, creating some of the most energetic phenomena in the universe. Magnetic field lines sometimes break and reconnect in explosive events that instantly convert stored magnetic energy into kinetic energy of charged particles. When oppositely directed magnetic field lines meet, they can suddenly snap and reconnect in new configurations. This magnetic reconnection releases energy that was stored in the twisted field configuration. The reconnection process accelerates particles to extremely high energies in very short time periods. Electrons and protons can gain speeds approaching light speed in a matter of seconds. These magnetic explosions occur throughout the jet formation region wherever field lines with opposite polarities encounter each other. Each reconnection event provides additional acceleration to the jet material. Magnetic reconnection helps explain the variable brightness observed in many black hole jets, as individual reconnection events create sudden increases in particle acceleration and radiation output. Jets aren't uniform streams of material flowing smoothly outward. Instead, they contain internal shock waves that act like cosmic particle accelerators. When faster-moving material catches up with slower-moving material in the jet, it creates collision fronts called shock waves. These shocks can accelerate particles to relativistic speeds through repeated encounters. The shock acceleration process works like a cosmic pinball machine. Particles bounce back and forth across the shock front, gaining energy with each collision. Some particles eventually reach speeds exceeding 99% the speed of light. Internal shocks also explain the flickering brightness of many jets. As different speed regions collide and create new shocks, the particle acceleration and radiation output varies dramatically over short time periods. The shock acceleration mechanism transforms the bulk kinetic energy of the jet flow into the random kinetic energy of individual high-speed particles. How do black hole jets maintain their narrow shapes across distances of millions of light years? The answer involves a delicate balance between magnetic forces and external pressure. Jets experience pressure from surrounding gas, trying to make them expand sideways. At the same time, magnetic forces within the jet create inward pressure that resists expansion. Magnetic hoop stress acts like invisible bands wrapped around the jet. These magnetic forces squeeze the jet material inward, counteracting the tendency to expand due to internal pressure. The balance between expansion pressure and magnetic confinement determines the jet's opening angle. Strong magnetic fields create narrower jets, while weak fields allow more expansion. Collimation efficiency affects how far jets can travel before dissipating their energy. Well-collimated jets can propagate across entire galaxy clusters, while poorly collimated ones disperse quickly. Jets moving at nearly light speed create one of the strangest optical illusions in astronomy. Their brightness appears to change dramatically depending on which direction they're pointing relative to Earth. When a jet moves directly toward us at relativistic speeds, its light gets compressed into a narrow cone by special relativity. This makes the jet appear much brighter than it actually is. Conversely, jets pointing away from us appear much dimmer because their light gets spread over a wider angle. The same physical jet can appear thousands of times brighter or dimmer based solely on viewing angle. This relativistic beaming explains why we see many more jets pointing toward us than away from us. It's not that jets preferentially point in our direction. We simply can't detect most of the jets pointing away. The beaming effect also causes apparent superluminal motion, where jet features seem to move faster than light speed, even though they're actually traveling slightly below light speed. The most stable and longest-lasting jets possess twisted, helical magnetic field structures that act like electromagnetic cables guiding the flow across vast distances. Helical fields form when rotation at the jet base creates spiraling magnetic field lines that extend throughout the jet's length. These twisted fields provide structural stability that prevents the jet from breaking apart. The helical structure also improves energy transport efficiency along the jet. Electromagnetic energy can flow along the spiraling field lines while maintaining the jet's collimation over enormous distances. Jets with strong helical fields can propagate across entire galaxy clusters without losing their coherent structure. Weaker or more chaotic magnetic fields lead to jets that dissipate their energy much closer to the black hole. The helical magnetic structure thus determines both the stability and the ultimate reach of black hole jets in shaping their cosmic environment. Black hole jets don't operate continuously like cosmic fire hoses. Instead, they turn on and off in cycles that can last anywhere from years to millions of years. Jet activity depends critically on the rate which matter falls into the black hole. When the accretion rate drops below a certain threshold, jets can shut off completely. Changes in magnetic field strength threading through the accretion disk also affect jet production. Weaker magnetic fields cannot generate sufficient magnetic pressure to launch material into jets. These interruptions explain why we observe jets in various stages of activity. Some black holes have active jets, others show remnants of past jet activity, and many show no jets at all. The cyclical nature of jet activity means that the same black hole can alternate between periods of dramatic jet production and quiescent phases lasting millions of years. Weak magnetic fields around black holes don't stay weak for long. The spinning accretion disk transforms barely detectable magnetic threads into cosmic powerhouses that control the entire feeding process. The disk doesn't rotate like a rigid wheel. Inner regions complete orbits much faster than outer regions. This speed difference stretches and winds up magnetic field lines like invisible rubber bands. Each rotation cycle wraps the field lines tighter and tighter. What starts as a weak magnetic whisper becomes amplified into a roaring electromagnetic storm. The field's strength can increase by factors of millions through this winding process. The amplified magnetic fields eventually become strong enough to compete with gravity itself. They can redirect matter flow, launch jets, and completely reshape how the accretion disk evolves. Differential rotation thus acts as a cosmic dynamo that converts the disk's rotational energy into magnetic energy powerful enough to dominate the black hole's immediate environment. Strong magnetic fields don't just thread passively through accretion disks. They push back against the gas with tremendous force, creating a cosmic battle between magnetic pressure and gas pressure. Magnetic pressure works similarly to gas pressure, but operates on charged particles instead of neutral atoms. Compressed magnetic field lines want to expand outward, just like compressed gas wants to escape from a container. When magnetic pressure becomes comparable to gas pressure, it fundamentally changes the disk's structure. The magnetic forces can puff up the disk, making it thicker than it would be under gravity and gas pressure alone. The balance between magnetic and gas pressure determines crucial properties like disk height, density distribution, and temperature profile. Strong magnetic fields create taller, more extended disk structures. This magnetic support helps explain why observed accretion disks sometimes appear thicker than theoretical models predict based on gas pressure and gravity alone. In the extreme environment around black holes, magnetic fields and plasma become locked together like dancers moving in perfect synchronization. This coupling fundamentally changes how material flows through the disk. The hot, ionized gas in accretion disks conducts electricity extremely well. This high electrical conductivity creates a phenomenon called magnetic field line freezing. Magnetic field lines become anchored to the plasma and move with it. When plasma flows inward toward the black hole, it drags magnetic field lines along for the ride. Conversely, when magnetic fields move or twist, they force the attached plasma to follow their motion. This frozen-in condition means that magnetic field geometry directly controls plasma flow patterns. Material cannot cross magnetic field lines easily. It must follow the field line topology like a train following railroad tracks. The freezing effect allows magnetic fields to guide and control the motion of matter throughout the accretion disk with remarkable precision. How does matter overcome its natural tendency to orbit and instead fall into the black hole? Magnetic forces provide the answer by stealing angular momentum from infalling material. All matter approaching a black hole carries angular momentum, the tendency to keep spinning or orbiting. This spinning motion normally prevents material from falling straight inward. Something must remove this angular momentum for accretion to occur. Magnetic stress acts like cosmic friction between different parts of the disk. Field lines connecting fast-moving inner regions to slower outer regions create tension that transfers angular momentum outward. As inner material loses angular momentum through magnetic stress, it can spiral closer to the black hole. The angular momentum gets carried away by the magnetic fields to outer regions of the disk. Without this magnetic angular momentum transport, accretion disks would remain in stable orbits forever and never feed the central black hole. Sometimes magnetic field lines with opposite orientations collide and create some of the most violent energy releases in the universe. These magnetic explosions can accelerate particles to incredible speeds in milliseconds. Magnetic reconnection occurs when field lines pointing in opposite directions encounter each other. The oppositely oriented fields cannot coexist in the same space, so they break and reconnect in new configurations. The reconnection process converts stored magnetic energy into kinetic energy of charged particles. Electrons and protons get accelerated to significant fractions of light speed during these explosive events. Each reconnection event releases energy equivalent to billions of nuclear bombs detonating simultaneously. The accelerated particles create bright flares that can be detected across vast cosmic distances. These magnetic explosions occur continuously throughout accretion disks, wherever oppositely directed field lines meet, providing ongoing particle acceleration that powers much of the disk's radiation. Magnetic reconnection doesn't just accelerate individual particles. It also creates coherent magnetic structures called plasmoids that get ejected from the disk like cosmic bullets. Plasmoids form when magnetic reconnection pinches off loops of magnetic field lines that become detached from the main disk structure. These magnetic islands contain trapped hot plasma and enormous amounts of stored energy. The plasmoids get accelerated along magnetic field lines that connect the disk to the jets. They travel outward at high speeds, carrying magnetic energy and hot plasma away from the black hole. When plasmoids reach the jet regions, they can trigger additional acceleration and heating of the jet material. Each plasmoid ejection creates a pulse of enhanced jet activity. This plasmoid ejection mechanism helps explain the variable brightness and structure observed in many black hole jets, as individual magnetic bullets create episodic bursts of energy release. Magnetic fields in accretion disks don't remain smooth and organized. Instead, they develop complex, chaotic structures that dissipate energy through a process called turbulent cascade. Large-scale magnetic instabilities break down into smaller and smaller structures, creating a cascade of energy from big to small scales. This process resembles how ocean waves break down into smaller ripples and foam. The turbulent cascade efficiently converts magnetic energy into heat that makes the disk glow. The chaotic magnetic motions also enhance the transport of angular momentum and mass through the disk. Magnetic turbulence operates on all scales simultaneously, from the size of the entire disk down to microscopic plasma scales. Energy flows continuously from large structures to small ones until it gets dissipated as heat. The cascade process helps explain how accretion disks can efficiently convert gravitational energy into observable radiation through the intermediate step of magnetic turbulence. The direction that magnetic field lines point relative to the black hole's spin makes an enormous difference in how efficiently jets form and propagate outward. When the magnetic field threading through the disk aligns with the black hole's spin direction, the jet formation process operates at maximum efficiency. The aligned fields can extract rotational energy most effectively. If the magnetic field points opposite to the black hole's spin, jet formation becomes much less efficient or may cease entirely. The misaligned configuration cannot tap into the black hole's rotational energy reservoir. The magnetic polarity also affects how tightly jets remain collimated as they propagate outward. Properly aligned fields create more stable, longer-lasting jets that can travel across entire galaxy clusters. This magnetic alignment requirement explains why some black holes produce powerful jets while others with similar masses and accretion rates remain relatively quiet. Accretion disks don't emit steady, constant light. Instead, they flicker with characteristic rhythms that reveal the magnetic processes occurring deep within their structure. These timing patterns, called quasi-periodic oscillations, arise when magnetic field configurations oscillate between different stable states. The magnetic modes create regular cycles of brightening and dimming. The oscillation frequencies depend on the magnetic field strength and the orbital motions near the black hole. Stronger magnetic fields create faster oscillations, while weaker fields produce slower cycles. By measuring these timing signatures, astronomers can probe the magnetic field structure and black hole properties that would be impossible to determine through other methods. The oscillations act like cosmic seismology. different magnetic modes produce distinct frequency patterns that encode information about the black hole's mass, spin rate, and magnetic field geometry. Magnetic fields don't just organize matter flow. They also regulate how fast black holes and their surrounding disks rotate by extracting rotational energy from both. Magnetic braking works when field lines connect the spinning black hole to the surrounding plasma. The magnetic coupling allows the black hole's rotation to drive currents in the plasma. These electromagnetic currents create forces that oppose the rotation, gradually slowing down both the black hole and the inner disk regions. The extracted rotational energy gets converted into magnetic energy that powers jets and heating. Over cosmic timescales, magnetic braking can significantly slow down rapidly spinning black holes. The spin energy that gets extracted provides the power source for long-term jet activity. The magnetic braking process creates a feedback mechanism that regulates the entire system, preventing runaway acceleration while maintaining steady energy output for millions of years. Spinning black holes don't just bend spacetime, they drag it along like thick honey stirred by a cosmic spoon. This effect, called frame dragging, fundamentally changes how matter and energy behave in the black hole's vicinity. When massive objects rotate rapidly, they twist the fabric of spacetime itself. Near spinning black holes, this twisting becomes so extreme that spacetime cannot remain stationary. The geometry itself gets pulled around by the black hole's rotation. Frame dragging affects everything in the black hole's vicinity. Orbiting material, light rays, and even empty space itself get dragged along with the black hole's spin. There's no way to remain completely at rest relative to distant observers. This spacetime dragging creates opportunities for energy extraction that don't exist around non-rotating black holes. The rotation literally drags energy outward through the twisted geometry. Frame dragging transforms spinning black holes into cosmic engines that can power jets and radiation through pure geometric effects rather than just gravitational attraction. Between the event horizon and a slightly larger boundary lies a region where the impossible becomes possible. Here, you could theoretically extract energy directly from a black hole's rotation and emerge with more energy than you started with. This region is called the ergosphere, from the Greek word meaning work sphere. Inside the ergosphere, spacetime rotates so rapidly that staying stationary becomes impossible. Everything must rotate with the black hole whether it wants to or not. The ergosphere's outer boundary marks where frame dragging becomes so strong that stationary observers cannot exist. This boundary lies outside the event horizon, creating a region where matter can still escape while being forced to rotate. Energy extraction becomes possible because rotation in the ergosphere can actually reduce a particle's total energy relative to distant observers. Objects can enter with positive energy and exit with negative energy. The ergosphere represents the only known region in nature where energy extraction from a black hole becomes theoretically possible without violating any laws of physics. Roger Penrose discovered a remarkable process that allows objects to steal rotational energy from spinning black holes. The method involves splitting particles at precisely the right location and trajectory within the ergosphere. A particle entering the ergosphere can split into two pieces with carefully chosen trajectories. One piece falls into the black hole along a path that reduces the black hole's rotation. The other piece escapes with more energy than the original particle possessed. The key lies in the geometry of spacetime inside the ergosphere. Certain trajectories have negative total energy relative to distant observers, even though the particles themselves have positive energy locally. When the negative energy particle falls into the black hole, it reduces the black hole's mass and angular momentum. Meanwhile, the positive energy particle escapes with energy extracted from the black hole's rotation. The Penrose process proves that black holes are not perfect energy traps. Their rotational energy remains accessible through clever manipulation of particle trajectories in curved spacetime. Magnetic fields threading through spinning black holes act like cosmic brake cables, gradually slowing down the black hole's rotation while powering intense jets of material. The braking occurs when magnetic field lines connect the black hole's ergosphere to the surrounding accretion disk. As the black hole rotates, it twists these field lines and creates electromagnetic tensions. These magnetic tensions extract angular momentum from the black hole and transfer it outward through the magnetic field structure. The black hole gradually spins down as its rotational energy powers jets and accretion disk activity. The energy extraction rate depends on both the black hole's spin rate and the strength of magnetic fields threading through the ergosphere. Faster spinning black holes with stronger fields produce more powerful energy extraction. Magnetic braking provides the primary mechanism by which spinning black holes power their jets, while simultaneously reducing their own rotation over cosmic timescales. Black holes can rotate at different speeds, from nearly stationary to spinning at the theoretical maximum rate. This rotation rate, called the spin parameter, directly controls how powerful the jets can become. The spin parameter measures how close a black hole comes to the maximum possible rotation rate allowed by physics. Non-rotating black holes have a spin parameter of 0, while maximally spinning black holes approach a spin parameter of 1. Higher spin parameters enable more efficient energy extraction through both the Penrose process and magnetic field interactions. Fast-spinning black holes can power jets that are hundreds of times more luminous than slow spinners. The relationship between spin and jet power explains why some black holes produce spectacular jets while others of similar mass remain relatively quiet. Rotation rate often matters more than black hole mass. Observations of jet luminosity thus provide indirect measurements of black hole spin rates, revealing that many supermassive black holes rotate at significant fractions of their maximum possible speed. The distance at which stable orbits become impossible depends dramatically on how fast the black hole spins. This boundary, called the innermost stable circular orbit, determines how much gravitational energy can be extracted from infalling matter. Around non-rotating black holes, stable orbits end at 3 times the event horizon radius. But for maximally spinning black holes, material can orbit as close as half the event horizon radius before becoming unstable. Closer stable orbits mean that matter can fall deeper into the gravitational well before being captured. This releases more gravitational energy per unit mass, making the accretion process more efficient. The efficiency gain from spin can be dramatic. Maximally spinning black holes extract 42% of infalling mass as energy, compared to only 6% for non-rotating black holes. Spin-dependent orbital changes explain why some accreting black holes shine much more brightly than others, even when consuming similar amounts of material. Black holes don't spin up indefinitely as they accrete matter. Instead, they reach equilibrium rotation rates where inward torques from accretion balance outward torques from magnetic braking. Accretion tends to increase black hole spin by adding angular momentum from the orbiting matter. The accreted material carries orbital angular momentum that gets added to the black hole when it crosses the event horizon. Magnetic extraction processes work in the opposite direction, removing angular momentum from the black hole through field line twisting and electromagnetic energy transport. These processes tend to slow down the black hole's rotation. The final spin rate depends on which process dominates over long time periods. Black holes fed by prograde orbits spin up, while those with strong magnetic fields or retrograde feeding spin down. Most observed supermassive black holes appear to have reached torque balance, spinning at moderate to high rates that represent equilibrium between competing angular momentum sources and sinks. When black hole spin rates change due to accretion or mergers, the resulting asymmetric mass motions generate gravitational waves that carry energy away from the system. Gravitational waves are ripples in spacetime itself that propagate outward at light speed. Any accelerating mass produces these waves, but the effects become detectable only for the most extreme astrophysical events. Changes in black hole rotation create time-varying gravitational fields that emit waves. The wave amplitude depends on how rapidly the spin rate changes and how much mass is involved in the asymmetric motion. During black hole mergers, gravitational wave emission removes significant amounts of energy from the system. The final merged black hole typically rotates more slowly than either of the original black holes. Gravitational wave detectors like LIGO have measured these signals from multiple black hole mergers, providing direct evidence of energy loss through spacetime distortions. Astronomers have discovered a remarkably tight relationship between black hole spin rates and the power output of their jets. This correlation provides strong evidence that jet energy comes directly from black hole rotation. Statistical studies of many black hole systems show that faster spinning black holes consistently produce more luminous jets. The correlation extends across enormous ranges in black hole mass and accretion rate. The relationship suggests that rotational energy extraction, rather than simple gravitational accretion, powers the most energetic jets in the universe. The black hole's spin energy reservoir dwarfs the energy available from matter falling inward. Some of the most powerful jets in observed galaxies require energy extraction efficiencies that can only be achieved through spin-powered mechanisms rather than conventional accretion processes. The jet power correlation has become a primary tool for measuring black hole spin rates indirectly, allowing astronomers to probe rotation even when direct measurements are impossible. The relative alignment between a black hole's spin axis and its accretion disk's orbital plane dramatically affects how efficiently energy can be extracted from the black hole's rotation. When the black hole spin and disk rotation align in the same direction, magnetic field lines can thread efficiently between the black hole and disk. This configuration enables maximum energy extraction in jet production. Misaligned systems, where the spin axis tilts relative to the disk plane, suffer reduced extraction efficiency. The magnetic field geometry becomes more complex and less effective at energy transport. Severely misaligned systems may produce weak jets or no jets at all, even if the black hole spins rapidly. The geometric relationship between spin and disk orientation often matters more than absolute spin rate. Disk spin alignment thus represents a crucial factor in determining which black holes become powerful jet sources versus those that remain relatively quiet despite rapid rotation. The laws of physics impose an absolute upper limit on how fast black holes can rotate. At this extremal limit, energy extraction reaches its theoretical maximum efficiency. Maximally spinning black holes, called extremal-care black holes, rotate at the highest rate possible without violating causality. At this limit, the event horizon nearly touches the ergosphere boundary. Extremal rotation enables energy extraction efficiencies approaching 42% of infalling rest mass. This represents the highest energy conversion efficiency possible for any known physical process in the universe. No mechanism exists for spinning black holes beyond the extremal limit. Additional accretion that would increase spin further gets rejected, and the black hole maintains its maximum rotation rate. Some observed supermassive black holes appear to rotate at near extremal rates, suggesting they have been spun up to their maximum possible speeds through efficient accretion processes throughout cosmic history. On April 10, 2019, humanity achieved something that seemed impossible just decades earlier. Scientists revealed the first direct photograph of a black hole's event horizon surrounded by its blazing accretion disk. The Event Horizon Telescope isn't a single telescope. It's a network of radio telescopes scattered across the entire planet, working together as one giant Earth-sized instrument. This technique is called Very Long Baseline Interferometry. The target was M87, a supermassive black hole located 55 million light-years away in the constellation Virgo. The image shows exactly what Einstein's theories predicted: a dark shadow surrounded by a bright ring of superheated material. The shadow represents the event horizon, where light cannot escape. The bright ring shows the accretion disk glowing at millions of degrees from friction and magnetic heating. This breakthrough image provided the first direct visual confirmation that black holes exist and behave exactly as theoretical physics predicted they should. Radio telescopes can see details smaller than anything visible to the human eye. By combining signals from telescopes thousands of miles apart, astronomers achieve resolution finer than reading newspaper text on the moon. Very Long Baseline Interferometry connects radio telescopes across continents to create virtual telescopes with unprecedented resolving power. The technique measures tiny differences in arrival time as radio waves reach different telescopes. This method reveals the internal structure of jets launched from black holes billions of light-years away. Astronomers can track individual knots of material as they accelerate from near-stationary speeds to 99% of light speed. The observations show jets accelerating gradually over distances of several light-years. Material starts slowly near the black hole, then gets accelerated by magnetic forces as it travels outward. VLBI studies have revolutionized our understanding of how jets form and maintain their structure across cosmic distances. When high-energy X-rays strike iron atoms in accretion disks, they create distinctive spectral fingerprints that reveal both the disk structure and the black hole's rotation rate. Iron atoms absorb X-ray photons at a specific energy corresponding to their K-alpha transition. This creates a sharp absorption line at a characteristic wavelength that acts like a cosmic barcode. Near rapidly spinning black holes, these iron lines get distorted by relativistic effects. The intense gravity and rapid orbital motion of the iron-rich gas broadens and skews the spectral lines in distinctive ways. The line profile reveals how fast material orbits at different distances from the black hole. From this information, astronomers can determine both the black hole's mass and its spin rate. The X-ray spectroscopy has measured spin rates for dozens of black holes, confirming that many rotate at significant fractions of their theoretical maximum speed. Black hole brightness doesn't remain constant. Instead, It fluctuates on timescales ranging from minutes to years, revealing how feeding rates and jet production are intimately connected. When more matter falls into the accretion disk, the increased friction and heating make the disk brighter across all wavelengths. Simultaneously, the enhanced magnetic field activity boosts jet power and luminosity. Astronomers monitor these coordinated brightness changes across different wavelengths simultaneously. Radio telescopes track jet activity, while X-ray satellites measure accretion disk emission. The timing correlations prove that jets and accretion disks are physically connected systems rather than independent phenomena. Changes in one component directly affect the other with predictable time delays. These variability studies provide the strongest evidence that black hole jets are powered by the accretion process, rather than by separate energy sources. Light waves normally vibrate in random directions, but when light interacts with magnetic fields, it becomes polarized, vibrating preferentially in one direction. This polarization reveals the invisible magnetic architecture of black hole environments. Polarized light from accretion disks and jets carries information about magnetic field orientation throughout these structures. Strong magnetic fields create highly polarized emission, while weak or chaotic fields produce unpolarized light. Astronomers use polarization maps to trace magnetic field lines from the inner accretion disk out through the jets. These observations reveal how magnetic fields get twisted and amplified as they flow outward. The polarization measurements confirm theoretical predictions about magnetic field geometry. They show orderly helical structures in jets and more chaotic fields in turbulent disk regions. Recent polarization studies of the M87 black hole revealed magnetic field structures that closely match computer simulations of jet formation processes. X-ray emission from black holes doesn't arrive steadily. Instead, it flickers with characteristic frequencies that encode fundamental information about the black hole's properties. These timing patterns, called quasi-periodic oscillations, arise from orbital motions and magnetic instabilities near the black hole. Different physical processes create oscillations at specific frequencies. The highest frequency oscillations correspond to orbital periods at the innermost, stable circular orbit. This frequency directly relates to the black hole's mass and spin rate through Einstein's equations. Lower frequency oscillations may arise from magnetic modes or precession of tilted accretion disks. Each oscillation type provides different diagnostic information about the system's geometry and physics. Timing analysis has become one of the most powerful tools for measuring black hole properties, especially for systems too distant for direct imaging. Some of the most energetic explosions in the universe occur when massive stars collapse into black holes and simultaneously launch powerful jets at nearly light speed. Gamma-ray bursts release more energy in seconds than our sun will produce in its entire 10 billion-year lifetime. These cosmic beacons can be detected from across the observable universe. The gamma rays are produced when relativistic jets from newly formed black holes slam into surrounding material. The collisions accelerate particles to extreme energies and generate the most energetic photons in nature. Different types of gamma ray bursts correspond to different black hole formation scenarios. Long bursts mark the collapse of massive stars, while short bursts indicate black hole mergers. These observations provide unique insights into jet physics under the most extreme conditions possible, revealing how matter behaves at temperatures and energies that cannot be replicated in laboratories. Ripples in spacetime itself carry messages about the most violent events in cosmic history. When black holes merge, they create gravitational waves detectable across billions of light years. The LIGO and Virgo detectors measure incredibly tiny stretches and compressions of space caused by passing gravitational waves. These instruments can detect length changes smaller than 1/10,000th the width of a proton. Each black hole merger creates a distinctive gravitational wave signature called a chirp. The frequency increases rapidly as the black holes spiral closer together before final coalescence. The gravitational wave signals reveal the masses and spins of the merging black holes. They also confirm that the final merged black hole rotates, providing energy that can power jets for millions of years. These detections have opened an entirely new window on black hole physics, allowing astronomers to study systems that produce no electromagnetic radiation. The apparent size of black hole shadows provides a direct test of Einstein's general relativity under extreme gravitational conditions. Theory predicts the exact angular size that a black hole shadow should appear based on its mass and distance from Earth. The Event Horizon Telescope measurements match these predictions with remarkable precision. M8A7's black hole shadow spans about 42 microarc seconds on the sky. That's equivalent to seeing a donut on the moon from Earth. The measured size confirms the black hole contains 6.5 billion solar masses. Future shadow measurements of other black holes will test whether general relativity remains valid under different conditions of mass, spin, and environment. These geometric tests provide some of the strongest confirmations that massive compact objects in galactic centers are indeed black holes rather than alternative exotic objects. Understanding black hole feeding requires observing across the entire electromagnetic spectrum simultaneously. Different wavelengths reveal different physical processes occurring at various locations around the black hole. Radio waves trace jet structure across vast distances. Infrared light reveals dusty regions in the outer accretion flow. Visible light shows the outer disk regions. X-rays probe the hottest inner regions near the event horizon. Coordinated campaigns use dozens of telescopes worldwide to monitor black holes simultaneously across all wavelengths. These observations reveal how different components of the system respond to changes in feeding rate. The multi-wavelength approach has revealed that jet activity correlates strongly with X-ray emission from the inner disk. This confirms that jets are powered by the accretion process rather than independent mechanisms. Simultaneous observations provide the most complete picture possible of how black holes transform matter into energy across their entire electromagnetic output spectrum. Jets moving at nearly light speed create dramatic optical illusions that depend entirely on viewing angle. The same physical jet can appear thousands of times brighter or dimmer based solely on its orientation. When a jet points directly toward Earth, special relativity compresses its light into a narrow beam that appears extraordinarily bright. This effect is called relativistic beaming or Doppler boosting. Jets pointing away from us appear much dimmer because their light gets spread over a wider angle. Most jets remain undetectable unless they happen to point roughly in our direction. This beaming bias explains why astronomers observe many more jets approaching us than receding. It's not that jets preferentially point toward Earth. We simply cannot detect most jets pointing away. The beaming effect also creates apparent superluminal motion, where jet features seem to move faster than light speed, even though they're actually traveling slightly below light speed. Material in black hole jets doesn't instantly reach maximum speed. Instead, It accelerates gradually over distances of several light years as magnetic forces continuously add energy to the flow. Radio telescopes can track individual bright knots of material as they travel outward through jets. These observations show material starting nearly at rest near the black hole, then steadily gaining speed. The acceleration typically occurs over the first few light years of jet propagation. Material reaches its maximum speed somewhere between 10 and 100 times the black hole's event horizon radius. Different jets show different acceleration profiles depending on their magnetic field strength and black hole spin rate. More powerful magnetic fields create faster acceleration over shorter distances. These velocity measurements confirm theoretical predictions about magnetic acceleration mechanisms and provide crucial tests of jet formation models. Galaxies should be producing stars much faster than they actually do. The mystery deepened when astronomers discovered that the most massive galaxies contain surprisingly few new stars despite having abundant raw materials. The solution involves feedback from active galactic nuclei. When black holes feed actively, their jets and radiation heat the surrounding gas to temperatures exceeding 10 million degrees. Hot gas cannot collapse to form new stars. This heating process operates like a cosmic thermostat. As the galaxy tries to cool down and form stars, the central black hole responds by increasing its activity and reheating the gas. The feedback mechanism explains why the most massive black holes reside in galaxies with the least active star formation. The black holes have effectively shut down their own food supply by preventing new star formation. AGN feedback represents one of the most important regulatory processes shaping galaxy evolution throughout cosmic history. Beyond individual galaxies lies a vast network of hot gas filling the space between galaxy clusters. Black hole jets reach into this intergalactic medium and fundamentally alter its properties across enormous volumes. The most powerful jets extend for millions of light years, far beyond their host galaxies. As these jets propagate outward, they deposit energy into the surrounding intergalactic gas through shock waves and turbulent mixing. This energy injection prevents the intergalactic medium from cooling and falling into nearby galaxies. Without this heating, central cluster galaxies would grow much larger by continuously accreting cooled gas from their surroundings. X-ray observations reveal cavities and bubbles in the hot cluster gas where jets have displaced material. These structures provide direct evidence of energy transfer from black holes to intergalactic space. The heating process maintains thermal equilibrium across galaxy clusters, preventing runaway cooling that would dramatically alter the cosmic distribution of matter. One of the most surprising discoveries in modern astronomy involves a precise relationship between black hole masses and the masses of their host galaxy bulges. This correlation suggests fundamental connections between black hole growth and galaxy evolution. Observations reveal that central black holes contain approximately 1/4% of their host bulge mass. This ratio remains remarkably constant across galaxies spanning enormous ranges in size and mass. The tight correlation implies that black holes and galaxies grow together through linked processes rather than independently. When galaxies undergo major star formation episodes, their central black holes gain mass proportionally. This coevolution occurs through feedback mechanisms that regulate both star formation and black hole accretion. Active black holes suppress star formation, while quiescent periods allow renewed growth of both components. The mass relationship provides strong evidence that black hole feedback plays a crucial role in determining final galaxy properties and limiting how massive galaxies can become. Stars create heavy elements through nuclear fusion, but those elements remain trapped inside galaxies unless something can transport them across cosmic distances. Black hole jets provide the primary mechanism for this cosmic element distribution. When jets propagate through galaxy clusters, they carry chemically enriched material from star formation regions into pristine intergalactic space. This process, called metal enrichment, distributes elements heavier than hydrogen and helium throughout the universe. The enriched material gets mixed with primordial gas that originally contained only hydrogen and helium from the Big Bang. This mixing provides the heavy elements necessary for planet formation and life in later generations of stars. Without jet-driven metal enrichment, much of the universe would remain chemically primitive. The elements essential for rocky planets and biological processes would stay locked inside individual galaxies. Jets thus serve as cosmic recycling systems that redistribute processed stellar material across intergalactic distances, enabling chemical evolution throughout the observable universe. When high-speed jets encounter resistance from surrounding gas, they create powerful shock waves that compress and heat material across vast regions. These terminal shocks represent the primary interface where jet energy gets transferred to environmental gas. The shock fronts form where jets decelerate upon hitting dense concentrations of intergalactic medium. The collision converts the jet's kinetic energy into thermal energy of the surrounding gas. Behind the shock front, turbulent mixing occurs between jet material and environmental gas. This mixing distributes both energy and chemically enriched material throughout large volumes of space. Different types of surrounding medium produce different shock structures. Jets in dense galaxy cluster cores create strong shocks with significant heating, while jets in sparse environments produce weaker interactions. The shock propagation process determines how efficiently jets can transfer their energy to surrounding material, making it the critical mechanism for black hole feedback on cosmic scales. Galaxy clusters contain enormous amounts of hot gas that should naturally cool and flow toward cluster centers. This cooling flow would feed central galaxies and fuel rapid star formation. But observations show this process gets dramatically suppressed. The suppression occurs through periodic heating by central black hole jets. Every few million years, the central black hole becomes active and injects energy into the surrounding cluster gas. This episodic heating maintains the gas temperature above the cooling threshold, preventing large-scale inflows toward cluster centers. The process operates like a cosmic pressure cooker that periodically releases steam. Without this heating, cluster centers would contain much more cold gas and exhibit far more vigorous star formation. The most massive galaxies would be significantly larger than observed. The cooling flow interruption demonstrates how black holes regulate their own growth by controlling the supply of material that could eventually feed them. While black hole jets typically suppress star formation through heating, they can paradoxically trigger star formation under specific conditions. When jet shock waves encounter dense molecular clouds, they can compress the gas sufficiently to initiate stellar birth. The compression occurs when shock waves from jets encounter pre-existing concentrations of cold, dense gas. The shock compression can push molecular cloud densities above the threshold needed for gravitational collapse. This process creates strings and clusters of young stars aligned with jet trajectories. These stellar nurseries provide observational signatures that reveal where jets have compressed molecular material. The triggered star formation typically occurs at moderate distances from black holes where shock waves have sufficient strength to compress gas, but not enough energy to completely disperse it. This mechanism represents a more subtle form of black hole influence, where the same energy that suppresses star formation in some locations actually enhances it in others. Black hole jets don't just affect gas. They can also gravitationally influence the orbits of entire satellite galaxies, potentially accelerating merger processes that would otherwise take billions of years. When powerful jets interact with the gravitational field of satellite galaxies, they can transfer momentum and alter orbital trajectories. These perturbations can cause satellites to spiral inward more rapidly. The orbital modifications depend on jet orientation relative to satellite positions. Jets aligned with satellite orbits provide the strongest gravitational kicks that accelerate merger timescales. More frequent galaxy mergers lead to rapid black hole growth as merging galaxies bring their central black holes together. This creates a feedback loop where jet activity promotes conditions for further black hole growth. The merger acceleration process may help explain why some galaxy clusters contain unusually massive central galaxies that appear to have grown through multiple merger events. The highest energy particles in the universe, called cosmic rays, require extremely powerful acceleration mechanisms to reach their observed energies. Black hole jets provide one of the few natural processes capable of creating these cosmic speedsters. Shock waves within jets can accelerate charged particles to energies millions of times higher than the most powerful particle accelerators on Earth. The acceleration occurs through repeated encounters with magnetic turbulence in shock regions. These ultra-high-energy cosmic rays travel throughout the galaxy and beyond, carrying information about their acceleration sites across cosmic distances. When they strike Earth's atmosphere, they create particle showers detectable by ground-based observatories. The cosmic ray production rate correlates with jet power, providing another connection between black hole activity and galaxy-wide phenomena. More active black holes produce more high-energy cosmic rays. Jet-accelerated cosmic rays contribute to heating and ionization of interstellar gas throughout galaxies, representing another pathway through which black holes influence their cosmic environment. In the universe's first billion years, most hydrogen existed in neutral atomic form that absorbed ultraviolet light. This cosmic dark age ended when something reionized the hydrogen, making the universe transparent to light. Quasar jets from supermassive black holes in the early universe contributed to this reionization process. The high-energy radiation and particles from these jets could ionize neutral hydrogen across vast volumes of space. While stars provided the majority of ionizing radiation, quasar jets enhanced the reionization efficiency by creating ionized channels that allowed stellar radiation to propagate further through previously neutral regions. The jet contribution was most important in dense regions where the first massive galaxies formed. These areas experienced enhanced reionization that facilitated subsequent star formation and galaxy growth. Early universe black hole activity thus helped create the transparent cosmos we observe today, demonstrating that black holes have influenced cosmic evolution since nearly the beginning of time.